Hello class, welcome to this last topic of input-output organization. As I said in the last lecture, that one term that has been repeating again and again was the buses. Whatever input-output operations we are talking about, it is all performed through buses. So this is a small topic. This is just a way of introducing you to the various types of buses, and it also introduces a very important topic, that is the bus arbitration. Now let's talk about that. See, we all know what a bus is. A bus is nothing but a common electrical pathway. If I take a single wire that connects a switch to a fan or to a tube light, that gives me one single pathway. But we have a common electrical pathway for controlling a number of components of the CPU, for controlling a number of electrical appliances. So that essentially makes up a bus. We have already talked about buses. You can have a system bus which is used to connect CPU to the various components, or you may have an internal system bus which is used to connect the various components within the CPU. Right? The internal system bus connects the control unit to the ALU to the memory unit, which is essentially made up of registers, whereas the system bus connects the CPU to the IO devices or to the memory devices. Right? So we can see this is the system bus which is connecting the CPU to the DMA controller to the memory to the IO devices. This is the system bus. Now the bus may be implemented in a number of ways. It may be implemented in the form of parallel lines on the circuit boards, normally called the ISA or the PCI bus, or you may have a ribbon cable. I don't think that many of you would have seen these two types of physical implementations. They are not part of your common laptops, but they were used in desktops, which we have used. I don't know how many of you have used, okay, how many of you have opened them up and seen these things, but they were there. Then we have strip connectors on the motherboards, and then we may have the external cabling, USB or firewire. Now this is something that you all might be quite familiar with. USB, we all know. USB for connecting our machines to the printers, or USB for connecting our phones to the chargers, or to the connecting our phones to the our laptops and all those things. So they are all buses. USB actually stands for Universal Serial Bus. So some basic characteristics of buses are, say, what does a bus do? There are multiple devices which are communicating over a single set of wires. One important thing, only one device can talk at a time or the message will be garbled or the message will be mixed up. Now this is a very important point. Only one device can talk at a time or the message is garbled. Just like if a number of people start talking in a class, what happens? It's not understandable what everyone is saying. Now, each line of wire of a bus can at any time contain a single binary digit. Now, a wire that is passing from a switch to a fan can either carry a 0, in which case the fan will be switched off, or it may carry a 1. So, these lines may and often do send information in parallel. You may have multiple lines which again send the data in parallel. A computer system may contain a number of different buses. We know we have the data bus, we have the control bus, we have the address bus, we have the system bus, we have the internal system bus, and so on. Right? So there are essentially four type of bus lines. In case of a computer, we have the data lines which actually tell to carry the data. We have the address lines which actually carry the address. We actually have the control lines which carry the control signals, and we may have power lines for carrying the power. Now this is the case in case of parallel. If we have serial buses, if we are performing serial input output, we don't actually need these three types of lines. So what happens is, in this case, data, address and control usually travel on a single wire sequentially. We can send data first, then address, or first address I can send, then I can send the control information, and finally I can send the data, right? Power lines obviously will be different. So again, a bus can be used for two type of operations. You can use a bus for sending the data or for receiving the data. But first, any device that is wishing to send the data or receive the data has to get the control of the bus. Why? Because there is a single bus, and any data, any device that wishes to use the bus for performing the operation needs to get the control of the bus. So sending data, the device needs to obtain the use of the bus, transfer the data via the bus, and then a possible acknowledgement from the receiver's side. If I'm requesting data, once again, the process will start with obtaining the use of the bus. Then I will send the request for data. Once again, the request of data will also go via the bus. It will go through the control lines. Wait for the other module to send the data, and there is a possible acknowledgement. I say possible acknowledgement because if I'm using handshaking, there may be an acknowledgement. If I'm using stroke, there might not be a acknowledgement. Now, while designing the buses for a computer, these buses, there are certain design issues, right? We have the bus may be dedicated versus multiplexed. We may have centralized versus distributed arbitration. This is something that we'll talk about later. We may have synchronous versus asynchronous buses. Then the bus width is there, the address bus width. We have already talked about this. The width of the address bus has a significant impact on how many memory locations can be addressed. The width of the data bus has an impact on how many bits of data can be carried at one point in time. So there are different transfer types are there: read, write, read, modify, write, read after write, block transfer, and so on and so forth. Now, let's talk about some of these design issues. You may have dedicated versus time multiplexed buses. Dedicated buses means you have a separate bus for control lines, you have a separate bus line for separate lines for control information, separate lines for data information, and separate lines for address information. Whereas in case of multiplexed buses, the same lines can be used for carrying address as well as data. Now they may use time multiplexing. Time multiplexing means that first data will be carried, then address may be carried, or the two informations may be multiplexed, may be interleaved with each other. The advantage of multiplex lines is obvious. You need fewer number of lines, but the disadvantage is that you have to have more complex control over the bits of information that is passing on the lines, whether it is address information or whether it is data information. Bus width, as we have talked about earlier, bus width has a significant role to play. Once again, let me repeat: the width of the address bus significantly or impacts the number of locations that your memory can actually have. Why? Because the width of the address bus decides how many memory location can be addressed. So that is why we have a limitation on the memory. The width of the data bus basically decides how many bits of data can travel at one point in time. So this again decides the performance of your computer. Timing, you have synchronous buses and asynchronous buses. Synchronous buses means when the same frequency clock, similar clocks provides the synchronization between all the bus operations. Asynchronous, that means there is no common bus clocks. They use handshaking. We have already talked about strobe and handshaking. Handshaking is actually used for completing an operation. So now, the computer devices. Now we can categorize computer devices into two categories. We have master devices and we have slave devices. A device that can request for the control of the bus, they are called master devices. These are active devices. Now another device which are passive and which are used and which simply respond to the requests of the masters, they are called the slave devices. Now CPU is usually always a master device. Memory can never be a master device. Memory always is a responder, never an initiator. Now this is a very important point because the device can be a master at one point in time, it can be a slave at another point in time. This is also important because at any given point in time, a number of devices may wish to become master devices, in which case arbitration has to come into play. Now, suppose there are a number of devices which need to become master of the buses at the same time. Say for example, the CPU is performing some operation, and at the same time the DMA controller also wishes to get the control of the bus for performing some operation. Let's take another example. Let us say there is a particular device which wishes to send some data to the CPU, and at the same time there is another device that also wishes to send some data to the CPU. Now both these devices or both the controllers want to be masters at the same time. Now who do we decide? So that is done with the help of something that is called bus arbitration. Let's talk about bus arbitration next. Now the bus arbitration. Now let's take a very simple example. Let us say I'm taking a class and two of you ask me, sir, we want to go out. And let us assume that there is a policy in the class, as you all might remember when we were young and we were studying in schools. Whenever you wanted to go out of the class, there was a rule that only one student can go out of the class at any one point in time. So suppose two of you say, sir, we want to go out. Now whom do I decide? Whom do I allow to go out first? So that is what arbitration actually means. Now, in this case, this example that I'm taking, if I'm the one making this decision, this is called the centralized arbitration. If you, among yourself, make this decision, who will go out first and who will go out second, then this is called decentralized arbitration. Now, static versus dynamic arbitration. Now, there are many facets to arbitration, right? Now, static versus dynamic arbitration basically means that we use something like a round robin allocation. Say for example, for understanding this, let's take once again the classroom analogy. Let us assume, I am sure that you people will identify with this. Let us assume that we have an out pass and a student has to get hold of that out pass before he or she can go out of the class. Now, one thing we can do is, in case of let us say a static system, I come into the class and I pass on the out pass to let us say roll number 1. Then the roll number 1 will shift it, pass it on to roll number 2, then 3, then 4, then 5 and so on. Let us say roll number 1 does not want to go out, so it simply passes on to roll number 2. Roll number 2 again does not want to go out, it passes it on to roll number 3. Now roll number 3 wishes to use the services of the out pass. So what it does, it takes the out pass and goes out of the class, performs the task, comes back and passes it on to roll number 4 and so on. Similarly, in case of static arbitration, the control of the bus is distributed among the various devices one by one by one. It follows a predetermined system, predetermined pattern. That means the control of the bus will also be given to a device which actually does not need the device, which has not requested for the device. So this system is not very efficient. On the other hand, if I talk about dynamic arbitration, now dynamic arbitration is done in response to a request. Now, this again is something like I keep the outpass to myself, and when one or more of you stand up and ask me, ki, sir, we want to go out, then I think about how to decide who to send out first. This is dynamic arbitration. So, in case of dynamic arbitration, the control of the bus, once again, it is given according to some policy, but it is initiated as a result of some request. Once again, centralized versus decentralized arbitration. Let us say if the decision about whom to send out is to be done by me, then it is called centralized arbitration. The decision about which device will be given the control of the bus, if it is done by a central arbiter or a central controller, then it is called centralized arbitration. Or let us say you people decide among yourself ki okay, if two people are standing, two people are asking to go out, whosoever has the lowest roll number will go out first. This is an algorithm that you might implement among yourselves. This is a decentralized arbitration. Now, decentralized arbitration, we have already talked about centralized versus distributed. Then there are other aspects over here. We have the allocation policies, we have the release policies, we have the request handling, we have the grant handling. Right? Let's talk about these. The allocation policies. Now, allocation policy means which policy is being followed for allowing a particular device the control of the bus. Now, the first thing that comes into mind is priority, right? Now, we may have a number of types of priority. The simplest is the fixed priority policy. Let us say if I implement the priority policy in the class that your roll number is your priority, and the smaller the roll number, the higher the priority. That means roll number 1 has the highest priority, roll number 10 has lower priority, roll number 20 has still lower priority, and so on. So whenever multiple masters request for the bus, the device which is having the highest priority will get the bus. But then again, there is a problem. Suppose a number of high priority devices keep on asking the control of the bus, the low priority device will never get the control of the bus. So it may lead to a situation called starvation. Starvation is a situation where the low priority device do not get the control of the bus. So how do we alleviate that? We may use something that is called a rotating priority policies. What it says, once a device has been given the control of the bus, its policy automatically becomes the lowest. Even if it was the highest priority device earlier, its priority automatically becomes the lowest as soon as it is given the control of the bus. So this is one way. Or what we can do is we can use something that is called the fair policies, which actually do not allow starvation. Say a simple example, all the requests that have been done in a particular time period will be satisfied, will be catered to first before accepting any other request. Or a bus request should not be pending for more than a particular amount of time. As the time passes, the priority of the request becomes higher. Or you may have a combination of these policies. Now, once the control of the bus has been given to a particular device, we have release policies also. Release policies simply mean, number one, do we take the control of the bus back from the device forcefully, or we ask the device to relinquish the control. If it is done forcefully, we call them preemptive policies. If we leave it to the device, we call them non-preemptive policies. Now, non-preemptive policies may be transaction based, one where the bus holder completes the transaction and then releases the control, or it may be a demand based where if there is another demand, then the bus holder will release the control of the bus. Now, any device which wishes to get the control of the bus uses two lines. One is called the bus request line and the other is called the bus grant line. The diagram that you are seeing in front of you is a centralized bus arbitration scheme called the daisy chaining. Now here the devices are given priority depending upon their proximity to the bus controller. Now this is a centralized bus arbitration because we have a common bus controller. Now, whenever devices generate bus requests, we have a common bus request line. So all the devices are connected to this. So this bus request line gets activated even if a single device is asking for the bus. Now, once the controller gets this bus request, it will give the bus grant to the device one. We can assume it is let us say it's a token. So the token is given to the device one. If it wants to use the token, then it will simply activate the bus busy line and use the bus. And if it does not, it will simply pass on the token to the next device and so on. One disadvantage over here is that the devices which are far away from the controller will get the control of the bus at a later time. Moreover, even if one of the devices in between becomes faulty, then the system breaks. The token will not be passed along further. Then the second way of arbitration is by using pooling, right? You can see over here, we have the various devices, we have the pooling lines, and this is the bus grant and bus request line. All the devices are connected. They are sending their bus request by the same line. Now this bus controller has some algorithm in place with the help of which it will decide which particular device to give the control of the bus. And according to that particular algorithm, it will decide upon the address of the device to which to give the control of the bus. These polling lines are used for that purpose. Now another option may be we may have centralized arbitration independent request. Now as you can see over here, each device has a separate request line and a separate grant line. These are the grant and request line for device 1, grant and request line for line device 2, and so on. Now the bus controller exactly knows which particular or which are the various devices which are requesting for the bus. And once again, based on some algorithm that is implemented within the bus controller, it will decide upon which particular device to give the control of the bus. Now, we can also have decentralized arbitrations. Now, decentralized arbitration means that the algorithm to implement the arbitration is implemented within the various devices. A very simple example is this decentralized daisy chaining method. Now this bus request line, as you see, is again common, and bus grant line, or here we call it the arbitration line, it's simply passing through all the various devices. Now these devices among themselves choose which particular device will get the control of the bus, right? So this essentially finishes our unit of input output organization, right? I'll upload these videos and schedule a class. Till then, bye.